We are Group 25 and today we will be demoing our AI-powered traffic system. This is our table of contents. Today, we will be demonstrating an innovative IoT project regarding smart traffic management systems. The current glide system in Singapore is unable to adapt to more complex situations, and our project aims to solve this. I will start by talking about our technology stack. Now, I'll be talking about our project overview. Our AI-powered traffic management system offers real-time analysis of road condition, precise vehicle counting, emergency vehicle detection, and dynamic traffic light optimization. These features ensure smoother traffic flow, preventing congestion, and enhancing road safety. Our system enhances efficiency by adjusting traffic light timings in real time, prioritizing emergency vehicle passage for rapid response, reduces emissions through smoother traffic flow. These benefits contribute to safer, more sustainable urban mobility. Now I'll be talking about our hardware and software. Our system relies on Raspberry Pi 4, Pi camera module, LoRa mesh network, and a server for traffic monitoring, data processing, and efficient communication between junctions. These components form the backbone of our AI-powered traffic management system. As for our software, we'll be using Python, C++, LoRa mesh, React, MongoDB, and Docker/Kubernetes. All these software power our system's data analytics, backend configuration, communications, user interfaces, database management, and scalability. With all these together, they ensure efficient operation and maintenance of our traffic management system.
After receiving the data, we perform data analytics on them and display them on a chart to gather these insights. It should also be mentioned that these data are updated through MongoDB change stream on the server, updating the data on the web in real time via WebSocket. Additionally, if you want to look at the raw data, you can view all of the records without any transformation. Next, we'll talk about the device setup.
So now this is how we will put on the Pi camera. First you going to catch and slot this in. You close the hatch. Then you see you can open. Next, you connect the microphone using USB. And that's how you set up the Raspberry Pi. Now we will connect the LoRa. First you connect the LoRa to the Arduino Uno. Then you connect the antenna. Connect the port. And then you can plug in to the Raspberry Pi. And that will be the controller Pi. On this screen, this is the configuration file of the object detection Pi. Our configuration files are done so that our main file can be standardized and used throughout all object detection Pi, and just use a config file to make change to necessary data that we need. The IP address detects the controller's Pi IP and broker IP address for MQTT communication, as well as the port and topic to allow what to subscribe and publish. As for direction, this is to determine the direction the Pi will be facing to perform our object detection. Next is the controller's Pi configuration file. Similar to the object detection Pi, we have the broker's IP address and topic to cater for the MQTT configuration. I include my own traffic ID and neighbor ID so that I can do it here instead of the main file.
So this is the configuration file for the LoRa. So LoRa actually has runs on the INO file, but then we have actually included a header file to actually manage all the configuration details. So we start off with the baud rate, and then we have the serial delay. So this is how frequently the LoRa radio posts the serial port to check if there's new packets that needs to be transmitted. And then we also have the payload length. So payload length is what's the maximum bytes that the Pi will send me for the payload to be transmitted. So in this case, it's 6 bytes. And then we also have the time to live. So time to live is actually how much forwarding the packet can take before it needs to be dropped. And then max adjacent traffic is basically how many neighbors you can have. So in this case, we have 4, because usually Singapore traffic junction is like a plus. And then these are the number of traffic IDs that you can have. And then the packet threshold is mainly used for timestamping. So basically, we drop all packets that are actually older or have the same packet ID number. So we only accept new packets and we only forward them. And then for traffic ID, so basically this part onwards is basically your own configuration. So traffic ID you set it to what your pi is. So if your pi is like traffic ID 2, then you set your LoRa radio for that pi to be traffic ID 2, and then your adjacent traffic ID is like north, south, east, west. So my north is traffic ID 1, my south is traffic ID 3, so on and so forth.
This is a bird's eye view on how our project will work using two junctions. On the top left hand corner, this is where we show the full integration of our project. Having one LoRa connected to a Pi, which we call the controller Pi, and 4 Raspberry Pi that is connected to a camera module and microphone. As mentioned before, each Raspberry Pi will face their respective direction, then connected to the controller Pi via MQTT, and from the controller Pi it will LoRa to neighbor junction, which is our outflow. What is so special about this is that we use object detection and sound sensor to detect siren and ambulance to know if there is an emergency vehicle passing through, where you can then send a signal to the traffic to determine if they can change the traffic flow.
Okay, so this is the controller Pi one. So as you can see here, the mosquito broker is currently running on this Pi, and then there are 4 object detection Pi over there, which is actually publishing to the mosquito server. And so if we were to run this server, it will actually start running the controller Pi code, which will actually publish this data. So if we were to look at this laptop that's simulating the server Pi, it's actually connected to a LoRa module, and then from there, if we were to run the code here, it will actively be listening. But the problem is that because the controller 1 is only neighbored to controller 2, and controller 2 is the one that's neighboring to controller 1 and the LoRa over there, so we actually have to run this controller 2 Pi in order to have the packets be forwarded from the controller 1 all the way to the server. This is to simulate like long distance communication. So from here, we can see that controller 2 actually receives information from controller 1. And likewise, we can see that controller 1 actually receives information from controller 2. And we can see that the server actually receives information on controller 1.
Now, we'll be sharing on our proposed solution.
So as you can see here, on controller 2, you can see that traffic ID 1 is constantly publishing, as traffic ID 2 is also constantly publishing. So on the server, we can see that we are receiving both traffic ID 1 and 2 packets. And then what that actually does is, it actually plots it into an analytical server where you can like have an overview of what's all the traffic count and all that. So then we have like different ways of viewing it. And then if you were to actually go into like the separate traffic IDs, we can see that this is the raw data that's actually being sent over. Yeah, so this is the historical data. So as for how the data is actually transferred over via LoRa, you can see that these are all counts, but we actually use ASCII characters or unsigned 8-bit integers to actually convert these integers into characters before transmitting them over. So if you were to see the Raspberry Pi that's connected to this LoRa module, the number is constantly changing. So actually they are converted to different type of ASCII characters, and then it's actually transmitted over. The ASCII characters are transmitted over. So this is how we are able to represent traffic count from 1 to 127. So because we need to have like a fixed integer size, so we have decided to encode our integer into ASCII characters before transmitting them over, such that we can represent each so north, south, east, west, right? So we can represent each direction in a single byte.
So this is our physical setup. This will be a traffic junction with 4 object detection pies. All 4 of them will look at all 4 lanes. So this is one of the pies, for example. It will actually detect the cars in the lanes, and it will sort them according to outflow and inflow. So in this case, you can see that they are all cars, or when it sends an ambulance, it will say ambulance detected. Okay, so now just to visualize what I was saying earlier, I'll run the code directly from here to see what the Pi is actually doing. So it's actually detecting the outflow of the traffic and the inflow of the traffic, and it's actually categorizing the cars and then the trucks, which in our case we'll be using ambulance.
In conclusion, this project facilitates an enhanced comprehension of real-time traffic conditions, enabling the dynamic adjustment of traffic signals alongside the provision of comprehensive analytics through a dashboard interface. This project's technology could be adapted for various contexts beyond traffic management. For instance, it could be utilized in urban planning to monitor pedestrian flow and optimize street layouts. Moreover, it could be applied in manufacturing facilities to monitor and optimize flow of goods and personnel as well. This is the end of our presentation. Thank you.